Hello everyone. Today here we are going to discuss about a very nice problem from Pathfinder. This problem is a multi-conceptual problem. So it depends upon two concepts. One is elasticity, another one is work power energy. So today we'll solve the problem step by step and we'll go further. Here is the problem statement. A light elastic cord of force constant K and relaxed length L is suspended from the ceiling. A bead of mass M threaded on the cord is held motionless close to the ceiling and released. If the bead slides down, the cord with a constant speed will be relative to the ceiling. Find the expression for the thermal power dissipated during the sliding of the bead. Right. This is a problem statement. So how to solve this problem? So how we can go ahead and we'll see. Here is the fundamentals we have to know regarding elasticity property. Right. Suppose for example, we have taken a wire of Young's modulus Y and cross-section area A, whose length is L, and we start applying two equal magnitude forces in opposite direction at their ends. So we are aware of already, like when we apply two forces in opposite directions of same magnitude, so it starts getting elongated or stretched, right? And it attains an equilibrium state after some certain point of time. And the new length of this one will be L plus delta L. And in this case, we can say that suddenly if you remove this forces, whatever we are applying externally, it is going to come back to its natural state. And this property we are going to call with a name, say it as elasticity of a body, we can say. And this is going to happen because of a force which is developed inside, which we are going to call with the name set as restoring force. The internal forces which are present inside the body and responsible for the body to come back to its natural state again, we'll call with the name set as restoring force. And we know already, like under equilibrium, the restoring force will be equal to the force applied, we can say it as. And from the properties of elasticity, we can say here that, right? So restoring force per unit area always will be equal to y into delta L by L, where y corresponds to Young's modulus of a wire, like which is the property of a wire, right? Okay. So different wires will have different Young's modulus. For a given wire, Young's modulus will be always same. We can say it as. So which implies here, right? Fr is equal to, so ya by L into delta L we can write. So F is equal to, we can write as ya by L into delta L we can mention. So this is what actually we can write it. Okay. And here also whatever the cord they have given, it is a light elastic cord of force constant K and relaxed length L is given. That means if you take this as a spring or spring constant K, and if change in length that is produced in this elastic cord is L, we can also write one more relation. F is equal to K into delta L we can write. So basing upon the equation 1 and equation 2 comparison, so we can write it as here. So K is equal to Ya by L, or so K into L is equal to Y into A, right? This is the most important relation we are going to have, right? Okay. And what this important relation says, if like you take any two wires or any two elastic cords which are made up of same material and same area of cross section, so always we can say like the force constant and the natural length of the wire, always their product will remain constant. And this is a very important property we are going to use in this problem. So always the product of force constant and natural length of any elastic cord will be always remain constant, provided that both materials must be made up of same nature and their area of cross section remains same. So here is the one of the important property we are going to use in today's problem. Now how to go ahead with the problem and how to get that answer step by step we will see. Now, so according to the problem basically, so we are having a bead, right, which is coming down, right, with a constant velocity v with respect to the ceiling here, right. Since mass of the bead is m. So if we write the FBD of the bead, we can say it as mg force will act. And due to some threading and other forces that may be acting on the bead due to the elastic cord, we can say let us those forces all sum together, it will be F, we can say. Since it is coming down with constant velocity, hence acceleration of bead must be equal to 0. We can say F is equal to mg, we can say. So this is one of the important thing that we can write. So this is equation 4, right? So like the sum of all downward forces and upward forces acting on the bead must be same, where F is equal to mg, we can say. So this F is the force, resultant force applied by the cord on the bead, we should say. Now, in the same way, what we can mention here also as, so if you take the cord, let us say, if you take the cord here, let us assume that this bead is here at some instant after the cord, okay? And if you take this portion of the cord here, concentrate on it, okay? So we can say some important points regarding this one, right? Right. If we take this portion of the wire, here we can notice that like the bead also will start applying a force called as F on this portion of the wire in downward direction. Okay, it's like basically like these two forces will be acting as an action reaction pair, due to which this wire will start getting elongated or stretched. We are going to mention it as. And please remember, right, okay, here, whatever the force F I have denoted, so it helps the elastic cord. It helps the elastic cord to get elongated or stretched. So that's what we can say it as here. Now, how to use this property and how to go ahead and all, we will see it. Okay. So suppose, for example, let us say, right, we were saying that as the bead starts sliding down, like this bead will start pulling this end, right, okay, of this one, and such a way that here this is going to get stretched. That means at any instant of time t, whatever this elastic cord will be there, this cord will be already in elongated state. You can say it is. Now, this is the most important fact we are going to use in this problem, and using this fact only we are going to go ahead. How to go ahead and all we will see. Okay. Let us assume let us assume K dash be the constant, the force constant of above shown chord, and L dash be its natural length, natural length. Then we can write basically here it is K dash L dash will be equal to K times L, we can say. So if you consider that here, like L dash be the natural length of this one. L dash is not the length. I'm saying L dash is the natural length of this part of the cord, and K dash be the spring constant or force constant, equivalent force constant of this part of the cord. We can write K dash L dash will be equal to K times L, where KL is nothing but the force constant of the complete cord and whose natural length is L. So this property we have taken from the elastic property already we have discussed in the step 1. Right. I hope all of you understood what I said. Right. Okay. So let us say here is the equation A we can write. Okay. And we can also say here, right, if X is the elongation that is already present, that is already present in the above chord at the above instant, at the above instant. So we can say, right, K dash X is the like equivalent force that is applied by the cord on that part of the bead when it's trying to stretch it. Okay. So which we can say it as K dash will be equal to mg. So let us name this equation as equation B. Children, these two equations are very, very important, and using these equations only we are going to go further. Okay. So K dash X is equal to M into G, we can say it as, right. Now, how to go ahead with the equations and how to solve the problem and all, we are going to see it in detail. Right. Now, let us assume let us assume after a time t, the after a time t, the bead has reached the above position. The bead has reached the above position. Hence, distance traveled by the bead. Hence, distance traveled by the bead will be. So, suppose for example, let us say we are having the bead, whatever it is there, which is sliding on the elastic cord. It has reached this position after a time t. Right, okay. Therefore, this is the total distance traveled by the bead during that time t, which we can say it as d is equal to vt, we can write. Since it is coming down or sliding down with a constant speed, we can write d is equal to vt. But what is this d? We can also write as. Already we discussed that this part of the cord is having natural length L dash and X is the elongation that has been produced because of the pulling force. So we can also write this distance is nothing but equal to L dash plus X. Hence, we can write one more relation or we can establish one more relation. L dash plus X is equal to Vt. So this is equation 3. Equation C, we can say. So these three are the primary equations we have to solve, right, the problem. So A, B, and C, these three equations we are going to use now, and we are going to see how the problem can be done, right? Okay. So what are the three equations we got? We can write it at stretch once. K dash L dash is equal to KL. Here KL is a constant. Next one is L dash plus X is equal to BT. This is the second one. And the next one, last one, we are going to say it as is here. It is K dash X is equal to mg. Okay, so K dash X is equal to mg. Now using these three, we are going to solve. How we can solve it and all we will see. Now from the first one and the last one, from the first one and the last one, what we can say, L dash by X is equal to KL by mg, we can write. So which implies, so L dash is equal to KLX by mg, right? Now substitute L dash in middle equation. Substitute the L dash in middle equation. So what we are going to get, we will see here. It is KLX divided by mg plus X will be equal to Vt, we can say. Therefore, X value will be, we can write it as mg Vt divided by KL plus mg. The simplification I'm not doing it, just we can write it as simply, right, whatever X value we are going to get, that is nothing but mg Vt by KL plus mg. Now, we already have KLX is equal to K dash X is equal to M into G, we can say. So K dash into MGVT divided by KL plus MG, which is equal to MG, we can write. Now we can write cancelling this MG and MG here. So hence what we are going to get from this one, we can write it as like, so K dash will be equal to, it is KL plus MG divided by VT, we can say. Now these are the next two important things which we are going to use, equation D, equation E. These two are the equations we are going to use indirectly in work energy power theorem, which we are going to apply here, and we'll get that answer. So what is the work energy theorem we are going to apply? How to get the desired answer now? We will see in detail. Right, okay. Suppose for example, we are having the bead which is sliding down the wire here with a constant velocity v, right? And here we will be considering the elastic cord plus bead as a system. If you consider elastic cord plus bead as a system, so what we can write according to work energy power statement here, it is work done by all external forces plus work done by any internal non-conservative forces must be equal to, so always change in mechanical energy we are going to get. So here I'm not going to go for derivation of this expression whatever we wrote, but this is a general expression we can write if you choose cord plus bead as a system. But if you have chosen the cord plus bead as a system, What are the forces that will be acting here? It is the ceiling will start applying a force at this topmost end here in this direction, because it will be in a stretched state, it will pull that topmost point. But here this force doesn't do any work here because the displacement of this point is 0, we can write. But apart from that, what is the other external force which will be acting on the system? Basically is gravity. Gravity is not a part, I mean, Earth is not a part of our system. So gravity will start pulling this bead down. Okay, hence, work done by the external force during a time t is given by. So the work done by external force here is equal to work done by gravity, which will be equal to mg into vt, we can say. So this is one more expression we are going to get. Therefore, we can write as mjvt plus work done by internal non-conservative forces is equal to change in mechanical energy of system. And sum of all kinetic energy and potential energy of system together, we are going to call with a name, say it as mechanical energy or total mechanical energy of the system. We are going to say it as. Please remember, right? Hence, what we can write here it is mgvt plus work done by internal non-conservative forces will be equal to, we can mention it as like always change in mechanical energy means change in kinetic energy plus total change in potential energy of the system. Here, they already mentioned that the bead is coming down or sliding down with a constant speed. Therefore, there is no change in kinetic energy of the bead. Apart from that, the given elastic cord is light. They mentioned it. So that means there is no mass associated with the elastic cord. Therefore, the kinetic energy of the total elastic cord at any moment itself is zero. So hence, basically, if the kinetic energy of the total elastic cord itself is zero, therefore there won't be no change in the elastic cord's kinetic energy. Therefore, this term is going to get cancelled. But we know that so during the sliding of the bead, like that bead is going to pull this cord down. Therefore, hence there will be some change in the potential energy or elastic potential energy of this elastic cord is going to take place. And how much change in elastic potential energy in the cord will take place? We can say it as delta U will be equal to half k dash x square, because like whatever the chord part we have taken, k dash is the equivalent force constant of that part. Therefore, k dash into x, because x is the already elongation that has been produced. So till that moment we have taken. So this is the potential energy stored. Therefore, delta U we can write it as it is half into. So what is k dash we have got? KL plus mg by Vt we got into what is x square, we can say m square g square v square t square divided by kl plus mg whole square. Already we got x value, right, that we have substituted here. So which we can write as delta u will be equal to, it is m square g square, we can write vt divided by 2 into kl plus mg. This is what we are going to get after simplification of this one. Now substitute this delta u and mg this in the above expression whatever we have already got. So what we are going to say it as it is mgvt plus work done by the internal non-conservative forces is equal to mg m square g square vt divided by 2 into kl plus mg, we can write. Okay, and work done by the internal non-conservative forces is equal to m square g square vt by 2 into kl plus mg minus mg vt we are going to get. So which we can write it as here, actually if you take work done by non-conservative forces, internal non-conservative forces, if you take it, okay, so we can mention it as, if we try to simplify the right side expression whatever we already have got. Okay, just you take mgvt common here, right? We are going to get mg divided by 2 into kl plus mg minus 1. If you take LCM and if you substitute and then simplify it, we are going to get it as it is mgvt into, it is 2kl minus, also I'm taking it as common, plus mg divided by 2 into kl plus mg. This is our expression we are going to get. Okay, so these are work done due to the non-conservative forces. Okay, therefore the work done due to non-conservative forces per unit time, which we can say it as it is minus mgv into, so 2kl plus mg divided by, we are going to write as 2 into kl plus mg, we can write. So this is the total work done So by the time duration of t due to the internal non-conservative forces, and these non-conservative forces like friction and all, they will be resulting in decreasing the total mechanical energy, or it causes the total mechanical energy of system is going to be lost again. And whatever loss in mechanical energy of system is going to take place, that will be coming out as thermal power here in this case. Hence, the answer for the question, right? The thermal power that is generated. So in the above time interval, we can write as it is mgv into 2kl plus mg divided by 2 into kl plus mg, we can say. So these is how we can solve this problem, students, right? This is the final answer for this problem. Hope you like the video, right? So kindly share and subscribe to my channel. Thank you.